Hello everyone. I am recording this stoichiometry video for you today because I am out of town and unfortunately we don't have time in our calendar to just not do anything. So we're going to do a quick review of mole-to-mole stoichiometry, which is what you learned last class. We started that with our s'mores lab and then we did move to mole-to-mole practice. This, if you want to look, is the last page of your mole-to-mole practice. Problem number 4. So I thought it would be a good place for us to start to work this problem together, and then we'll shift into the content for today, which is mole to gram stoichiometry. I can't tell you how important it is that you understand this topic, that you do the work that I'm asking you to do, and that you practice, even if it means outside of class. We will find that we have, in addition to this stoichiometry, we have solution stoichiometry, we have gas stoichiometry, we have thermochemistry stoichiometry. So this topic isn't going away. And I would really rather see you learn it up front as opposed to struggling with it through all the rest of the year. So let's take a look at reaction 4 down here. And if I look at this equation, I see that we need to balance this reaction. So if I put a 3 here, then I have 3 hydrogens, so 6 hydrogens, which means I need a 3 here. I have 1 aluminum, 3 oxygens on the left, 3 oxygens on the right. So our coefficients are 3, 1, and 3 and 1. Is this reaction redox? Well, this is a double replacement reaction, so no, double replacement reactions are not redox reactions. Okay, so what is the theoretical yield? I want to point that out to you. Theoretical yield in moles. That means if we're operating in a perfect world where we're in the lab and there isn't human error and our equipment didn't have limitations, how much should we be able to make? So that's thing 1. We're going to calculate this. Theoretical yield means calculated. So what is the theoretical yield in moles of aluminum bromide when 0.97 moles of hydrobromic acid reacts with 2.25 moles of aluminum hydroxide? So I hope that you realized right away that we're given 2 numbers, which means we're going to have to work 2 different problems, and then we're going to have to figure out what our answer is based on our problems. So whenever you have 2 numbers, you have to work 2 of these problems. So I'm going to come down here and draw my little map, and I'm going to put 0.97 moles of HBr up in the top corner. And obviously I know that if I have moles of HBr up in the top corner, moles of HBr has to come diagonally down. And I'm looking for moles of aluminum bromide. So moles of aluminum bromide goes in the top. Now, this is a spot that we have open, and we get those numbers from our mole ratios. So I'm going to look back at my balanced reaction, and I see that the coefficient for aluminum bromide is a 1. So I put a 1 in right there. And then I see that the coefficient for HBr is a 3. So I put a 3 here. The 3 numbers that we have in our problem are the 0.97 moles of HBr that we started with, the 1 in front of the aluminum bromide coefficient up in our reaction right here, and the 3 in front of HBr right here. Okay, so I'm going to go ahead and I'm going to delete those so that we have some room to work our next problem. Now, when we've set it up this way, moles of HBr cancels, and we're left with moles of aluminum bromide, which is what we were asked to find. So now, if I say 0.97 times 1 divided by 3, we will have our answer. So now I realize that my calculator is in the other room. I'm recording this at home, and I'm going to go grab it. So I want you to do the math, 0.97 times 1 divided by 3. I will be right back. Okay, so 0.97 divided by 3. Okay, that's what you should have typed into your calculator. And I get 0.32 moles of aluminum bromide. Okay, so I've worked my first problem. Now I have to do it again, and I have to start with the second given. So 2.25 moles of aluminum hydroxide. So my moles of aluminum hydroxide have to come diagonally down. That pattern never stops. And I'm looking for the same thing. I'm still looking for moles of aluminum bromide. So again, I look to my coefficients. The coefficient for aluminum bromide is a 1. The coefficient for aluminum hydroxide is also a 1, which means that I can make 2.25 moles of aluminum bromide. So I have two numbers. The question is, which one do I actually make? Well, I hope you remember that we always make the smaller of the two numbers. So I would actually make 0.32 moles of aluminum bromide because I run out of HBr first. So my HBr is my limiting reactant. My excess reactant is my aluminum hydroxide. And now I have to figure out, well, how much remain? Because I had enough aluminum hydroxide to make this 2.25 moles of aluminum bromide, but I only made 0.32 moles. Okay, so now is when we take our problem and we work backwards and we say, well, I have 2.25 moles Actually, I'm going to change how I started that. I'm going to start with my 0.32. I'm always going to start with my answer from my previous problem. Okay, so this answer comes right here. There are several ways that you can work this. If you find a way that works for you better, you're welcome to use it. This is just the way I like to teach it. So I'm going to start with how much product I actually made, which means my moles of aluminum bromide have to come diagonally down. And what I want to know is, well, if I only made 0.32 moles of aluminum bromide, then how many moles of my aluminum hydroxide did I actually use? So I'm going to look back up at my coefficients. My aluminum hydroxide is a coefficient of 1. My aluminum bromide is a coefficient of 1 as well, which means that I used 0.32 moles of my aluminum hydroxide. Okay, these moles cancel out. So this is used. So if that's used and I started with 2.25 moles of it up in my problem and I subtract my 0.32 moles used, so 2.25 minus 0.32 gives me 1.93 moles remaining or moles left. Okay, so the key takeaways here. Theoretical means calculated, doing what we just did. Two starting numbers means two stoichiometry problems. The answer is always the smallest. And the reactant that started your stoich problem to give you your smallest answer is your limiting reactant. To find the moles of the excess reactant, you start with how much product you could actually make. We're trying to see how much of that excess reactant we actually used, and then we subtract. Okay, so our lesson today is going to build on this problem that we just solved. So we've already learned that when we go into the lab, we can't measure things in moles. We don't have a tool that does that. But we do have a tool that measures things in grams. So at this point, we're going to start to add in molar mass, so that we can convert our moles to grams. So if you'll turn the page, these are going to be mole to mass or mole to gram conversions. Okay, so we have this first reaction up here. We have two nitrogens Nitrogen plus 3 hydrogens gives us 2 ammonias, and that is a balanced reaction already. This is a redox reaction because it's a synthesis reaction. Okay, so part A, let's read it and see what we have. If we have 7 moles of nitrogen, okay, one number, reacting with 3 moles of hydrogen, second number, how many moles of NH3 will be produced? So I'm given moles and I'm asked to find moles, which means we're going to do the kind of problem that we just worked together just a minute ago. And because I have 2 starting numbers, I have to work 2 problems. So I'm going to try and make this fit the space a bit better. So we have 7 moles of nitrogen. And I'm going to bring my moles of nitrogen diagonally down. And I'm looking for, right here, looking for moles of NH3. So that's my unknown. Okay, the numbers that go in here in these blanks come from the coefficients of the reaction. So the coefficient for NH3 is a 2, and the coefficient for N2 is a 1. So my moles of nitrogen cancel, and I say 7 times 2 is 14 moles of NH3. So I have enough nitrogen to make 14 moles of ammonia. Let's see how much ammonia we can make with 3 moles of hydrogen. Let's start our second problem. We have 3 moles of hydrogen. Moles of hydrogen comes diagonally down. I'm still looking for the same thing, moles of NH3. My unknown doesn't change. So I look back up to my reaction. Coefficient for NH3 is a 2. The coefficient for hydrogen is a 3. Moles of hydrogen cancels. So we say 3 times 2 is 6, divided by 3 is 2. So we can make 2 moles of NH3 with the hydrogen that we have. So then the question comes, well, which one do we actually make, 14 or 2? Answer is always the smallest one. So we will make 2 moles of NH3. We have enough hydrogen to make 2 moles, and then it stops. So hydrogen is limiting. We have enough nitrogen to make 14 moles. So we have plenty of nitrogen. That's our excess. So if we are given grams instead of moles, we will use molar mass to convert. Okay? And as a reminder, molar mass is where you take the chemical formula, you look at the periodic table for each element and add up the total, which reminds me, I need to pull up the periodic table for us to look at as we're working through this lesson. Okay. So now, how many moles of hydrogen gas for part B? So I'm looking for moles of hydrogen gas, that's my unknown, are needed to react completely with 2.35 grams of nitrogen gas. So even though I have 2 numbers here, I don't have 2 numbers here. Sorry, I only have 1 number here. I have 2.35 grams of nitrogen gas, and I want to know how many moles of hydrogen gas I can make. So I'm going to start a stoichiometry problem, and I'm going to put my 2.35 grams of nitrogen right here. And then because grams of nitrogen is up in the top, then grams of nitrogen has to come diagonally down. Converting from grams to moles is molar mass. So the mass of nitrogen, of 2 of them, is 14.02, I believe. Yeah, 14.02 grams. And that is equal to 1 mole of nitrogen. So what I want you to see is that this right here is the molar mass conversion that we've been using since the beginning of the year. Okay, that part isn't new, converting grams to moles. Now, once we have converted our grams to moles, we pick up with what we learned in our mole-to-mole stoichiometry. We bring moles of nitrogen diagonally down. Okay, so always diagonally down, top to bottom. Okay, so moles of nitrogen comes diagonally down. We're looking for moles of hydrogen. The numbers come, when you have moles over moles, come from the balanced coefficients. So the coefficient for hydrogen is a 3. The coefficient in our reaction for nitrogen is a 1. So grams of nitrogen cancels, moles of nitrogen cancels. All we're left with now is moles of hydrogen, which is what we were asked to find. The math of this says 2.35 times 1 times 3, 4.02 times 1, and then divide the 2. If you're going to use your calculator and do it all in one big calculation, make sure you're using parentheses around your numerator and your denominator. So when I do that math, I get 0.50 moles of hydrogen. So we started with grams of nitrogen, converted our grams of nitrogen to moles of nitrogen, and then used our stoichiometry, moles over moles, to convert to moles of hydrogen gas. Okay, well, what if we are asked to solve for grams instead of moles? In other words, if we're given moles to start with and we want to know how many grams that makes, then again, we use molar mass to convert. So, problem C. How many grams of ammonia, NH3, can be produced? So I'm looking for grams of ammonia. So this time, instead of looking for moles, I'm looking for grams. So how many grams of ammonia can be produced from 0.75 moles of hydrogen gas and excess nitrogen? Whenever you see excess, cross it out. We have plenty of it. We don't have to worry about running out of it. We don't even need to think about it. So I have one number. I'm starting with moles, and I'm converting to grams. So my 0.75 moles of hydrogen gas goes first. Then I bring my moles of hydrogen gas down. This is just a simple mole ratio like we learned last class for mole to mole stoich. Okay, so my moles of unknown, in other words, moles of ammonia, go up here. These are the coefficients then that I'll put in these blanks. So the coefficient for NH3 is a 2. The coefficient for H2 is a 3. So now if I've stopped, I've converted my moles of hydrogen to moles of NH3. But the problem asks for grams of NH3. So I know that I have to come over here and I have to put molar mass in here. So my moles of NH3 come into play down here, diagonally down from top to bottom, and grams of NH3 goes up top. So this is molar mass, which says that 1 mole is equal to the mass of NH3. So nitrogen's mass is 14.07, and I can tell you I already made a mistake in problem B. Wow. Okay, so I thought the mass of 1 nitrogen was 7, but it's 14.01 times 2, which means we need to go back and change this to 28.02. I'm so sorry, guys. So let me recalculate that number. I hope that some of you caught that, even though I wasn't there in class. So 28.02 means our answer is 0.25. I guess I should have known I could just cut that in half. So 0.25 moles of hydrogen. Okay, so 1 nitrogen is 14.01, and I have 3 hydrogens. So the molar mass of NH3 is 17.04 grams. Okay, so this right here is molar mass. Okay, So the math of this is 0.75 times 2 times 17.04 grams divided by 3 times 1. Okay, so I'm going to put that in my calculator using parentheses around the numerator and the denominator. I get 8.52 grams of NH3. Okay. So, other than my mistake with the molar mass in the previous problem, here's what I want you to see. When you start with grams, you use molar mass like this. And when you start with moles, then you have your molar mass here. So it's the same thing, just added on either end of your mole-to-mole stoichiometry conversion problem. Okay? All right, so let's work one more together. Potassium nitrate, KNO3, decomposes to form potassium nitrite and oxygen gas. So let's write the reaction. So if we look at this, we have KNO3, and it's decomposing to form KNO2 and O2. Okay, the reason I have this 2 right here is because oxygen is one of our 7 diatomics. Let's make sure our reaction is balanced. And it is not, because I have 3 oxygens on the left and 4 on the right. So if I put a 2 here, and then I put a 2 here, now I have 2 nitrogens and 2 potassiums, and I have 2 and 2 is 4, 5, 6 oxygens, and I have on the left 2 times 3 is 6 oxygens. So let me make this a little bit more legible for you. This goes here, and then we'll have a 2. All right, this is redox because it's decomposition. So let's write our mole ratios. Don't forget the order matters. So KNO3 to KNO2 is a 2-to-2 ratio. Y'all, I know we're in the habit of simplifying, but just please don't simplify your mole ratios. It just makes it makes you more likely to make a mistake. So KNO3 to O2 is 2-to-1, and KNO2 to O2 is also 2-to-1. So now our question is asking us, how many moles of potassium nitrite, KNO2, so I'm looking for moles, are produced from 4 grams of potassium nitrate? Got to be careful on this one not to mix up your nitrate and nitrite because they're very similar. So I'm given grams and I'm looking for moles. That means it's like this problem right up here, problem B. Okay, so we're going to use molar mass first because we're given grams. So I'm going to find molar mass for potassium nitrate first. Potassium is 39.01. Nitrogen is 14.01. Oxygen, okay, let me type that in again. My calculator had turned off. 39.01 plus 14.01 plus oxygen is 16, and there are 3 of them. So 3 times 16 gives us a molar mass of 101.02. So this was 39.01. Nitrogen is 14.01. Okay. And oxygen is 16 times 3. And we get 101.02 grams. Okay, I'm working at the very bottom of my iPad screen, so it's kind of getting mad at me. So 4 grams of potassium nitrate, KNO3. Okay, so grams of KNO3 comes diagonally down, and I know I'm going to use molar mass, so this is moles of KNO3. 1 mole, our 101.02, gets put right in that blank. And now I have converted from grams to moles. So now I'm going to finish my mole to mole conversion and bring my moles of KNO3 down, and I'm looking for moles of KNO2. So my coefficient for KNO2 is a 2. Coefficient for KNO3 is also a 2. Cancel out moles of KNO3, and we're left with what we were looking for. So 4 times 2 divided by 101.02 times 2 gives us 0.039. 0.0395, so I would probably round it to 0.04 moles of KNO2. Okay, so let's turn the page. How many grams of oxygen gas? So we're going to continue using that same reaction. Okay, so we're gonna have to flip back and forth a little bit. So grams of oxygen gas is what we're looking for, are produced from 4 moles of potassium nitrate. So I'm starting with moles and I'm asked to find grams. That means it's going to be like part C down here. Starting with moles, finding grams. So our molar mass is going to be the last thing that we use. Okay. And grams of oxygen gas, well, oxygen is 16 times 2, means our molar mass is 32 grams per mole. So I'm going to start my dimensional analysis problem, and I have 4 grams of KNO3. I have to bring my grams of KNO. Oh, I messed up, y'all. I'm sorry, I'm making mistakes on this today. I have 4 moles of KNO3. So moles of KNO3 comes diagonally down. Okay. This is my mole ratio. So moles of what I'm looking for, oxygen gas, are in the top. So I come and I look at this reaction. The coefficient for oxygen is a 1. The coefficient for KNO3 is a 2. So 1 and 2. So if I stopped now, I would have converted my moles of KNO3 to moles of oxygen. But I'm not done because I'm asked for grams of oxygen. So I bring my mole of O2 diagonally down, gram of O2 in the numerator. So 1 and 32. So moles of O2 cancel, and we're left with grams in the numerator. So 4 times 32 divided by 2. So 64. We can make 64 grams of oxygen gas. Now, have you noticed the pattern that when we are doing mole to gram conversions, we have 1 box, 2 boxes, and 3 boxes every single time. So if you're given moles and asked for grams, or you're given grams and asked for moles, you can automatically know that you're going to be drawing out a Stoich problem. Let me draw that where it's a little bit easier for you to see. You're going to be drawing out a Stoich problem, and you need to fill those spaces. You can always draw 1 horizontal line and 2 vertical lines every single time, if it's mole to gram or gram to mole. Okay, all of our mole to mole conversions, you'll notice the ones that we did here, only have 2 boxes. So this one here, and then this one here. Okay, mole to mole, 2 boxes. Mole to gram, gram to mole, 3 boxes. And I want to show you our stoichiometry map. Okay, so if you start here at grams of given and you go to moles, that's 1, 2, 3 boxes, just like I showed you a second ago. If you're starting with moles and going to grams, that's 1, 2, 3 boxes. So you can use your Stoich map to tell you how many boxes you need in your problem. And if you're starting with moles and going to moles, 1, 2. And in fact, these things down here even tell you what form you need your molar mass in. Moles in the numerator and grams in the denominator. Okay, so don't forget to use that Stoich map. It's really helpful. All right, now you have some practice to do. You have practice on this page and you have more here. Okay, 3 pages. I thought we were done with just 2. The only way to learn this skill is to practice it. We will quickly be done with stoichiometry. We have skills checks, we have mastery checks. So I want you to use your classroom time wisely so you don't have to work outside of class and get these practice problems completed. You can check your answers with the key on Canvas. If you have any questions, I'll be back on Monday. Love to help you out in tutorials or advisory.